Okay, so this project we've set up here is again using the blade antenna. So the first step is just your definition. You import your Feko model. When you hit the import variables button, it generates this list. So these 4 variables are parametric geometric variables in Feko. And here you can define the range that you'd like to use. So these variables have just been normalized so that their normal value is 1. So we're looking at about a design space of a 30% swing on each of the variables. Then this model was set up before the post-Feko integration was available. So we used the Lua script functionality. So I have a script that is run in the background, and this basically writes or creates this output file that is read by HyperStudy, which contains literally these 4 different variables. So those are values that are calculated by the script and written to these variables. And that is the real impedance, the imaginary impedance, S11, and bandwidth. And all 3 of those first parameters are at the center frequency. The bandwidth is the 10 dB bandwidth. So yeah, that's everything for the setup. The next step here is to basically configure the DOE. And this is also really straightforward. There's only really one parameter that you need to choose. So firstly, there are many different methods that you can apply for space filling in HyperStudy. But we would always or strongly recommend the use of MELs for 2 reasons. Namely, it's very efficient for space filling operation, but it also has the property that it can be extended. Where you might need that is once you've created your fit surface response, you can see how accurate that is, and you may need to add additional simulation points. And in that case, you don't need to recompute the first data set. You can just add a new data set to extend that. So yeah, literally the only value that you need to set here is decide how many runs to run, and it's a little bit complicated depending on the complexity and the behavior of the antenna in the design space, and also obviously the number of variables. So in this case, we ran 250. After you've run the simulations, you get a table, so you can see these are the geometric variations, and these are the results of all those parameters. Now, already at this step, HyperStudy has some very nice tools for kind of investigating the design. One of these is the Pareto plot. So I'm looking at my 4 output responses, and as a function, we sort of plotting the geometric dependence on those variables. So if we just glance at these 4 plots, what you might notice is that in most cases, the W3, I think that's one of the widths for the blade underscore SF, is actually the smallest influence on the design, except in this case, where it's a little bit bigger, but all the values are actually quite small here and dominated by this variable. So in this case, it might be possible to reduce the dimensionality of this design space to only use these 3 variables. So that's one really nice parameter. Another thing you can do here is look at the behavior. I think I've already set some up here, where you have a kind of snake pots, and you can really play around to get a feeling how the responses interact with the geometric variables. So that's the first DOE. I have also run a second DOE, which is just a validation DOE. You don't need to do the step, but I just wanted to demonstrate it nonetheless. Here we use a different method just to generate statistically independent data, and we use many less number of samples here. And I'll show you in a moment where that comes out. Then we generate our surface response. And this is also a matter of a few mouse clicks. We firstly need to point or add our DOE matrices. The main being our input DOE, which is the main computation. And here you can see the validation matrix, which I'm using for testing purposes. Then in the definition, I think it's in specifications. So again, HyperStudy has a whole range of options how you can go about computing the surface response, but in a relatively new release, they included what's called the fast surface response. And basically what that does is it goes through all the different methods that are available and chooses the optimum or the best fitting surface response to the data. So it's basically fully automated. There are some options that you can configure, but to date I've never used any of those. So the recommendation is use fast, you press apply, you press next, and it computes for you. And yeah, so let's have a look what we get from that. So firstly, you have kind of an integrity. This is just sort of a high level summary. It gives you some sort of range parameters. I think most interesting starts with the diagnostic, which is where you can get a sense of the accuracy. So here you can see the 4 different output parameters, and our R-squared parameter gives us an indication of accuracy, where ideally we would like that to be 1. So as close to 1 as possible, the more the accuracy. So in other words, all these parameters have been fitted really nicely or very accurately. And here in the detail view, you can also see where that testing matrix pops out. So HyperStudy does do some cross-validation using the first or main DOE, but this is just a sort of additional step that you can use if you want. The last thing here you can just see is the type of fit surface that was used. So radial basis function for the first 3 and MLSN for the bandwidth. Here you're already fairly confident that we have a good accuracy, but you can also look on the residuals. So here we're looking at S11. On the left column, we have our the actual simulated values. On the right, we have the values at the same. I'm just going to add the geometric variables here to make it a bit more clear. So at this instance of the geometry, we have the computed value by Feko and the value obtained from the surface at that point. And here you can see then the error. So a very small error also expressed as a percentage. And we can really look down the whole list there and see, as we expected, a very small error is occurred here. Then 2 last thoughts here, starting with the scatter. Let's do this on the surface rather instead of the actual data. So what we're looking at, and this really highlights the need for trade-off analysis, the computed S11 and our bandwidth on the lower axis. So a classic optimization scenario might be you want to maximize your bandwidth, but you want to minimize your S11 at the center frequency. So you see that is sort of a conflicting requirement somehow, because as your bandwidth increases here, the trend is that your S11 also goes up. So this is sort of a classic multi-goal optimization problem. How do you go about setting up your goals? How do you weight your goals to get the optimum that you're looking for? And we'll get into that in a little bit more detail in a moment. But just to show you one more feature here is the trade-off analysis that you can do manually at this point. So we have slider bars at our disposal here for the geometric variables. And as I'm changing those, you may have noticed that the output responses are updating. So we can pretty easily play around to get a feeling how my geometric variables interact with my output responses. And the reason why this is so quick is because those values are simply being read from my surface response. And that is really now the value of this workflow, is that we have a continuous behavior. So we don't need to rerun simulations each time. We can just go and get the value from the surface for each of those responses. So in that regard, now if we start looking at optimization, we can run these really fast optimizations, and it gives us the flexibility when we are doing things like trade-off analysis to play around with my goal weighting and things like that. So what I've done is set up 3 different optimization problems. Let's start off looking at the goal of each of those optimizations. So again, you can see my responses. You'll notice that there's this field evaluate from, and I've chosen to evaluate that from the fit surface response. So it means that instead of computing each iteration, it's just going to get those from the surface response. And in this case, we're just minimizing S11. The second optimization is more of a trade-off. So I'm going to limit S11 to be below 0.3, but I'm going to maximize my bandwidth. And then just for a novel idea for the third case, I have decided to, let's say, change the characteristic impedance of this antenna. So instead of using a 50 ohm real part, I've gone and looked for a 75 ohm real part. So just to give you an indication how fast this really is, you'll see here there are going to be 50 iterations performed. I'm just going to press apply to reset that. Going to press next and evaluate, and you'll see this is really a matter of seconds, and we have found an optimum down here. And again, the reason why this has been so fast is instead of computing all of those, it's just gone and got those values from the surface. And the last step, what you can do, you can select a row or just one of those values and press verify. And what that'll do is it'll create a single instance where that Feko model is prepared with that geometry. You can rerun those and then compute the actual responses. And I've done that already just to show you quickly how that looks. So here you can see the 3 different designs. We're looking at S11, starting off with our min S11, the way we minimized our S11 at the center frequency. Then the second curve, or the green curve, is where we reduced S11, I think below 0.3, but also try to maximize the bandwidth. And you'll see we have probably about 20 or 25% more bandwidth for this case. And the last case is then where we retuned the characteristic impedance to 75, or the real part of the impedance to 75 ohm. What's interesting here is if I just change the characteristic impedance to 75, you can see, so the optimization is done at 300 megahertz there. But incidentally, we have actually a really nice bandwidth at this behavior as well. And obviously we can look at the impedance plot for that last case as well. So we optimized for 75 ohm, and more by chance, it just happens that the imaginary part is pretty close to 0 there too. And that's why we have a really nice deep S11 there.